subscribe and turn on the notification bell so that you can get updated every time I post a video. So here we're going to look at one of the questions under or another question under circular motion. The question says, a belt runs on the wheel of a hammer mill of radius 20 centimeters. During this time, the wheel takes to coast uniformly from an initial speed of 5 revolutions per second, 30 meters of belt length over the wheel. For this wheel, find A, the number of revolutions. Question A, find the number of revolutions it turns while stopping. 2, or B, deceleration of the wheel. 3, or C, time taken to come to rest. So this is the question that we're going to consider answering in this video. So here we have the data. Let's come up with the data that we're given. We are told to say a hammer mill of, okay, so this is a radius, 20 centimeters. This can be expressed in meters, which will be 0.2 meters. Then the other information that we have is the initial speed, which is 5 revolutions per second. Then we have L, the belt length, which is 30 meters. What else are we given? Okay, I think this information is sufficient. So now, the first question demands us to find the number of turns or the number of revolutions it turns while stopping. Revolutions. Let me erase the first part. Now, the angle through which the wheel turns is theta is equal to 2 pi a. So this is the angle through which the wheel turns. Now, this is the pi having a value of 2 or 3.142 or 22 over 7, and this is the number of turns. So let us keep this equation. But remember, the number of turns is related to L by this relation, 2 pi r, the number of turns. So the length over perimeter, which is 23.87. These are revolutions. So this one, it is the same as, it can be rounded off to 24 revolutions. So this is the number of turns. Now, putting this into this, we are going to have theta is equal to 2 pi times 24. This will give us 150 radians. So this is in terms of this. So this is the angle through which the wheel turns after covering a belt length of 30 meters. Then this one is the angle in terms of radians, which is covered when this is achieved, or rather when this length of hammer mill belt is covered. So the number of revolutions or the number of turns is 24 revolutions. So we can now go on to, so this is the part A. Number of revolutions. Okay, so number of revolutions, we have this one. Then we are going to find deceleration of the wheel. We know that theta, which can be, okay, we make this the subject. So this one will be minus this one square. We're going to get to alpha theta. We divide by 2 theta. Also here by 2 theta. This one and this one will go, this one and this one will go, and we're going to remain with alpha is equal to, now plugging in the values for this one, we know that. So this one, in terms of radians, this one we have 150 radians into this. Then for the five revolutions that we have, so omega initial is equal to 5 revolutions per second. So this one we can multiply it by 5 real times 2 pi rad over 1 revolution per second. What we're going to get is 1.24 radians per second. So this is what we're going to have. So plugging in this one here, we're going to have, when it comes to rest, deceleration, when it comes to rest, we have the final will be 0 minus. So this one squared, 1.42 squared over 2 theta, 150.8. What we are going to get is negative 3.27 radians per second squared. So this is the deceleration that we are going to get after putting in all the values, all the necessary values. So from this part, or from this point, we find now the time taken to come to rest. So we know that omega is equal to omega initial plus alpha t. And this one, we can next the subject. This will be like this. Then here we are going to have over alpha. So plugging in the values, we have here, when it comes to rest, it is 0. Then the initial angular speed is 31.42, which is this one, radians per second over negative 3.27 radians per second squared, the unit. So from this, we can even round it off to time is equal to 10 seconds. So this is the value. Thank you so much for watching the video.